Welcome back to class number 4. We're in the bonus round of extra examples coming from Cengel. Here's Cengel's example 3.8, where we're approximating the compressed liquid. Actually, did I even do this one? I'm asking myself. I'm not asking you. Sure. No, did I? Yes, I did. Okay. Determine the internal energy of compressed liquid water at 80 degrees Celsius and 5 megapascals using A, data from the compressed liquid table, and B, saturated liquid data. What is the error involved in the second case? Okay, so there's actually some stuff to be learned here. So I decided to go ahead and do it. I originally crossed it out on my page, said, nah, I don't need to do that one. So, but let's try to do this one anyway. So, okay, so first, let's go, given the information we have at 80 degrees Celsius and 5 megapascals, let's go to table, we already know it's probably compressed liquid. It already says compressed liquid. So let's go to table, I didn't write table, I can't write the word table, I'm very tired. And check that one out. So B14, be kind. Okay. So we have, what do we say? 5,000, no, they said 5 megapascals, which is 5,000 kilopascals, which is right here. Okay. And what we said, the temperature is 80. So we're talking 333.69, 333.69. So at P is equal to 5,000 kPa, because that's what we used, and T equals 80 degrees Celsius, we get U of 333.69 kilojoules per kilogram. This is a measure of how the molecules are bouncing off of each other. They're really good. They're feeling bouncy here. And so that's the first one, right? That's part A. Yeah, from the compressed liquid table. That's what we did. Now I go to so this is A, really. Maybe box it. Table B.1.2. So what they're saying is saturated liquid data. So let's check that one out. And they said 2, right? So that means that it's the one that's indexed by the pressure. So we're looking here. Here's the 2. We go down here, 5,000, right in there. And internal energy, you can't really quite see the top of it right here. Here's internal energy. Here's the fluid internal energy. All right, so we go down and index that one to 5,000. That's not very good. All right, so let's write that down. There we go. At P equal to 5,000 kPa. T sat is equal to 263.99 degrees Celsius. That's a good thing to know. And the U of the liquid, which is the F, one right there, 1,147.8 kilojoules per kilogram. And that does not, that's no good. That is not a good measure right there as an approximation. So we're asking saturated liquid data, right? So so maybe what we should do is now we would look to, and they said, they didn't say what table to go to. I guess I said what table to go to. Let's take it out for, so let's go to B.1.1. And let's go to the temperature at 80 degrees Celsius, right? so here's 80 degrees Celsius right in there. And you can see the absolute pressure. That's 47.39, much, much smaller than 5,000. But let's come back over to here and go to 80 right here and see 334.84. Huh. Let's write all that stuff down. We got PSAT, which is 47.39 kilopascals, and UF is equal to 334.84 kilojoules per kilogram. Wow. Good. Smiley face. Tongue sticking out. Smiley face, tongue sticking out. Yeah, look, check it out. What's the conclusion there? That maybe the internal energy is more closely associated with the temperature than it is with the pressure, right? Right, because we could say, oh, maybe the pressure doesn't quite nearly matter on this as much as the temperature does. That's a interesting observation, and maybe one to keep in your head. If you were going to compare these two values to each other, I would say that the percent, and you're going to, let's consider this one to be an accurate one, because this is at the pressure and temperature that we were destination. This is just an approximation just based on the temperature alone. So like we could say, we'll take the one that we know is, call it accurate, call it like, it's just more representative. That's probably the thing. And we'll divide by, there should be another 3 in there. We'll divide by that one. So we can see that we get a negative 0. Oh, I didn't do this well. 3446E3. I don't know if I did. Anyway, I think I got that right. 0.345% less than, or we could say that B.1.1 is less than B.1.4. Maybe that's one way of saying it, right? Because this one is less than that one. That's with the negative, and we're making a comparison to this. So the language, when you're making a comparison, does count for something. It does convey what was taking place. You don't necessarily just arbitrarily pick what the bottom one was, and you want to have a statement afterwards of what that comparison means, because the comparisons are quite often where most of the knowledge takes place. The actual values for things can drift all over the place, but usually the comparison of the thing has more useful information. So let's see if we have. Do we have one more in our tank? I don't know. What do you think? Can we do one more? I'm tired. I gotta grade, and I gotta do something else. I can't remember what the other thing was. I gotta write a solution to a homework problem. I think I just wrote the homework. Did I write the homework problems? I can't remember if I wrote the homework problems or not. Oh boy, I'm getting tired. Okay. So anyway, this is the. I'm not gonna write the whole thing out. I'm just gonna show it to you. All right. So here is the problem that we just worked on. Let's see. Did I just work on that? I'm so tired. Okay, that goes back over here. All right. So we have the use of the steam tables to determine properties. So we start out with all these empty blanks right in here. And so here's one where we're going to be given the pressure, and we're going to be given the quality. So we know it's going to be saturated because that's the only way that we have a quality. They also want us to find internal energy, which is totally fine here. So what we're going to do with this one is we're going to look up in the saturated tables, and probably in B.1.2 because it's indexed by pressure. We can find the temperature, and then from here we can find the fluid internal energy and the fluid, the gas minus fluid internal energy, the UFG. Multiply that and we'll get it. All right, so giving away the store here, that's what we'll do, right? So we look it up at that pressure. Here's that temperature, so we can put it into there, and then we can use the quality along with the fluid and the gas minus fluid internal energy, and we can enter in there, and that's going to be liquid and vapor. All right, what happened here? So we get that one done. Cool. Here we have a temperature and an internal energy. So we're not sure if it's this one's liquid and vapor. We're not sure if this one's still liquid and vapor or whether it's superheated. It could be. So what we want to do is first look up table B.1.1 for that temperature. Here's the saturation pressure. We don't know this, but we might. This might be the thing that's going to be. It depends whether the thing is superheated or not. So we're still going to look. But we go ahead and do look at the internal energy, and it's in between the fluid one. I didn't bother to write it down, and the fluid minus gas one right there. So we know that we can use that information and solve for that X and find that's 53.5%. So that's what we can put back up into this table, that it's a liquid and vapor combination. Here's the 53.5. And this right here is the saturation pressure that gets placed into there. So boom, we got another one of those done. Now we go to this next line, and we're given 1,000 kilopascals and an internal energy here. And we still, once again, we don't know whether it's going to be a superheated condition or whether it's going to be saturated and wet and somewhere in between. So the first thing we do is look up in the B.1.2. Here's the saturation temperature, but look at here. Here's the internal energy, and the internal energy for a gas is this, but we wanted 2950, right? So 2950 is greater than that, therefore it's superheated. And so we go ahead and go look in the superheated at 1,400, and we find that 2,957, that's very close. And that might be pretty close for mere mortals. But we can also check out the one nearby, and we can see that it's actually the 2950 is between the 2957 and the 2875. So we go ahead and do an interpolation, and we find, yeah, it's almost 400. 395.7. So that's a significant difference enough, 496 compared to 400, that it was worth doing it, right, to interpolate and find out what that temperature was going to be. And now we have 1D, and now this is just out of hand, right? We're getting out of hand. We have a temperature and a pressure, which is almost always probably likely going to be superheated. But we'll go ahead and check the saturated ones first. And but we don't. Oh, look! We were wrong, right? Because we had a temperature of 75 and a saturation pressure of 38.58, and the problem had it 500 kilopascals. So the pressure's higher, therefore it's a compressed liquid. So we look it up in at the 500, and we note that we don't have 75 for the temperature. So, but here's the internal energy between these two. So we could go ahead and look up for 75 what the internal energy is going to be, and that is 313.8. And then I think for the last one right here, we are given that it is 850 kilopascals and it has a quality of 0. That means it is completely a liquid. So we just have to look that up in the temperature tables right here. And well, in the pressure tables. Yeah, in the pressure tables, sorry, because they gave us 850 kilopascals. So 850 kilopascals. There's the saturation temperature, and there is the fluid internal energy. So there was a lot of stuff to do in this, but we could do it pretty quickly because I already wrote it all down, right? But I mean, we just have to be able to think through. I want you to be able to do any of these problems, and this should probably be right. Saturated liquid, right there. Saturated liquid. This is something that you should be able. All of these should be things that you can do. Ta-da.